The exploration of replicating human taste perception through a combination of chemical test kits and artificial intelligence unfolds in a series of steps designed to mimic the natural tasting process. The initial phase involves developing chemical test kits that emulate the functionality of human taste buds. These kits are engineered to identify the 5 basic tastes: sweet, salty, sour, bitter, and umami. Each detector is specialized for a specific taste, mirroring the selectivity of receptors in human taste buds. The human tongue is an intricate chemical analyzer. This extraordinary organ does more than detect flavors. It serves as a pathway for transmitting detailed information about our dietary intake directly to the brain. The brain's crucial role extends beyond differentiating between tasty and distasteful foods. It also involves appreciating the subtle flavors and characteristics of various foods and beverages. This sensory skill varies among individuals, with some possessing remarkably refined palates that enable them to perceive subtle differences in taste and quality that might go unnoticed by others. The intriguing research question of whether machine learning algorithms can mimic or even surpass the human brain's capacity to distinguish the quality of food and drink has driven our investigation. In our research, we have found that this is indeed possible, and we have successfully achieved it. We began by training AI with quality information on a scale from 1 to 10. Alongside the chemical analysis results of wine samples, this approach aims to equip the AI with a foundational data set that mimics the process of wine evaluation typically undertaken by renowned critics and professional judges. The challenge is to replicate the detailed and sophisticated process of wine assessment traditionally performed by experts who have established high standards in the industry. Their evaluations, grounded in years of experience and a deep understanding of wine's subtleties, set a benchmark for quality. Our first question was to determine whether AI, through machine learning algorithms, can rival the extraordinary palate of human wine experts by leveraging both sensory data and chemical composition analysis. For our training, we utilized logistic regression, decision trees, random forest, and support vector machines. The highest accuracy was achieved with the random forest model. We then assessed this model's accuracy with 320 wine samples, attaining an accuracy rate of 72%. This means our trained AI correctly predicts the quality of 72% of the test wine samples. Moreover, it closely estimates the remaining 28%, exhibiting a very low mean squared error of approximately 0.63. By the end of our first project, we had created what could be considered the premier red wine quality assessor, capable of evaluating wine quality better and faster than any human expert. In just 2 seconds, our AI can deliver test results for 320 wine samples. Additionally, we observed that our AI maintained high accuracy levels in predicting wine quality, even when limited to only 4 variables. This model, effectively replicating a perfect wine expert, still achieved a 72% accuracy rate under these conditions. This result was particularly fascinating, considering that since the first use of wine in Iran and Georgia around 6000 BC, the critical variables for assessing wine quality have remained a mystery. For much of its history, wine quality was assessed solely through sensory evaluation, sight, smell, and taste. In the 19th century, scientific analysis of wine made significant advancements with the introduction of the first acidity tests. It was always assumed that all 11 variables were critical for accurate assessment. Yet, before our eyes, our wine expert replicator achieved amazing accuracies even without all 11 variables. This led us to question how we might determine the importance and criticality of each variable in relation to one another. With the best wine expert now at our fingertips, we considered whether we could devise a methodology to assess the critical value of each chemical input variable by asking our AI wine expert thousands of questions. Thus, our follow-up project was conceived. Uncorking AI's elegance, mastering precision in pivotal variables, defining wine quality via incremental analysis of baseline accuracy. Before initiating our follow-up project, we analyzed numerous papers on the critical variables for assessing wine quality. These studies approached the question but had not empirically or conclusively determined the criticality of input variables for a perception akin to human evaluation of wine quality. Other research often relied on educated guesses about the importance of variables based on observations. Our follow-up project distinguishes itself by implementing a thorough methodological framework named Incremental Analysis of Baseline Accuracy. This approach identifies the chemical variables most predictive of wine quality and aims to streamline the predictive process by pinpointing key variables that significantly influence quality assessments. Our project has demonstrated the feasibility of a methodology that precisely determines the criticality of chemical inputs, including their exact values and their importance order, to identify which inputs significantly contribute to the quality assessment of sensory perceptions, such as taste. Through our follow-up project, we have shown that it is possible to quantify qualitative aspects like taste perception, which is often thought to be accessible only through subjective evaluation. Our findings challenge traditional assumptions about sensory analysis by systematically quantifying such perceptions. After we first trained AI with 1,280 wine samples, we developed a methodology for questioning our AI wine expert replicator and performed calculations after each query. Our dataset included 320 test samples, each with the 11 input variables and one quality measure. Aiming to evaluate how accurately our wine expert replicator could respond, we explored the full range of combinations of these input variables, totaling 2,047 combinations excluding the empty set. We questioned all combinations for each of the 320 wine samples, repeating the process 5 times for reliability. With this methodology, we have assessed the criticality of each variable with a precise criticality number for the first time in the history of wine, which we will present shortly. In our research, we explored the complex mathematics behind machine learning applications that assess wine quality. Today, during this presentation, we will summarize our main findings. We introduced the concept of baseline accuracy, defined as the inherent predictive ability of our AI wine expert replicator. Impressively, without any specific input data, this system accurately identified the quality of 40% of the wine samples. These predictions were not mere guesses. The AI made informed estimations on 320 samples without direct information by leveraging foundational knowledge from its training on 1,280 samples. This initial exposure provided the AI with experience in understanding the distribution of wine quality, enabling it to solve the mathematical regression formula representing this distribution accurately. For context, making random guesses in this scenario can be likened to asking a wine expert to guess the quality of wine without smelling or tasting it. In similar blind tests, human experts typically achieve about 10% accuracy. This comparison highlights our AI's superior predictive capability, a phenomenon we've termed baseline accuracy. It underscores the AI's ability to use its training to make educated guesses about wine quality, establishing a knowledge baseline that far exceeds human intuition. We conducted a critical variable analysis by analyzing over 2,047 combinations of input variables. This method quantified the impact of each variable on the AI's predictive accuracy. identifying those that significantly increased accuracy from a baseline of 0.4 to 0.75. Through incremental analysis, we have assessed the cumulative importance of each variable and evaluated them to determine their relative criticalities. This marks the first time such a detailed and empirical evaluation of variable criticality has been conducted in the domain of wine quality assessment. The insights we share today not only highlight our AI's capabilities, but also represent a significant advance in understanding the complex variables influencing wine quality. For the first time in wine history, we reveal the critical variables, properly ordered and weighted.